A good knowledge of tides is fundamental to safe and efficient navigation in tidal waters because many harbours are tidal, which means that they cannot be entered at all states of the tide, and it's necessary to perform calculations before entering or leaving in order to avoid running aground. Also, tidal streams have an enormous impact on passage planning and can create unpleasant or even dangerous conditions, especially when wind and tide are in opposing directions. We all know that the surface of the sea continually rises and falls. This movement is the result of tidal forces attributable to the gravitational pull of the moon and the sun. The lowest point in the cycle is called low water, and the highest, high water. The interval between low water and high water varies, but in most parts of the world is around 6 hours and 13 minutes. So there are 2 high tides and 2 low tides on average every 24 hours 51 minutes, with the time of high water and low water getting progressively later each day. The heights of high water and low water also change. Take a look at this graph for Portsmouth for the period 0000 hours on 14th of August to 2400 hours on Friday 16th of August, courtesy of the UK Hydrographic Office EasyTide website. See how the time of the early morning high water moves back each day. The difference between the height of high water and low water is called the range. The range between high water at 0445 and low water at 1000 on the 14th of August is 2.9 meters, whereas the range between high water and low water the following morning is 2.4 meters, and 2.2 meters the next day. The reason for this variability is the ever-changing position of the moon relative to the Earth and the Earth to the Sun. The moon orbits the Earth approximately once every 28 days, and the combined centers of gravity of the Earth and Moon orbit the Sun approximately once every 365 days. The orbits are elliptical and are not exactly in plane. The Earth's center of rotation is also inclined to its orbital plane. The whole system takes 18.6 years to complete its cycle, and this period is known as the tidal epoch. If we ignore the Sun for a moment, you can see that the gravitational attraction between the Moon and the Earth will result in the surface of the oceans rising towards the Moon. The surface of the oceans is also raised on the opposite sides of the Earth. The reason for this is less obvious. Imagine a line equidistant between the points on the Earth nearest and furthest from the Moon. As you travel from this line towards the Moon, the gravitational pull increases. As you travel from the line away from the Moon, the pull decreases. This results in the oceans rising simultaneously on both sides of the Earth. When viewed from the North Pole, the Earth rotates anti-clockwise once every 24 hours. So, if the Moon was stationary, any given location on the Earth's surface would experience high water, low water, high water, low water, once a day. However, the Moon is also moving, travelling 1/28th of its orbit of the Earth every day, and 1/28th of a day is 51 minutes. So on average, the tides get 51 minutes later every day. That's all well and good, you might say, but I've sailed along the northern Gulf of Mexico, in Thailand, or southeastern Australia, where there's only one high water and one low water each day. And in other parts of the world, notably along the central south coast of the UK and on parts of the Dutch coast, there are multiple high or low waters. How come? It's because water, when confined to a space and in motion, has a natural period of oscillation that depends on the shape and dimensions of the space. For example, water in a small bowl will oscillate with a shorter period than water in a large one. Ocean basins act like giant bowls. Each has its own period of oscillation. Furthermore, each sea, bay, sound, and strait modifies the characteristics of the larger ocean basin of which it is a part. So virtually every place on Earth has a unique tidal pattern. Tides in places only a few miles apart may differ radically in both time and range. Some basins have sizes and shapes that are more responsive to the moon's forces. Others respond more to the sun's forces. Some respond equally to both. The Bay of Fundy between Nova Scotia and New Brunswick is a classic example. It's just the right length such that its period of oscillation fits almost perfectly with the period between high and low water. So it amplifies the tidal range, which would otherwise be less than a metre, giving differences between high and low water of over 16 metres at its extreme northeastern end. On the flip side, the Mediterranean is constricted by the Straits of Gibraltar at its far western end, and on its own isn't large enough to raise significant tides according to the gravitational pull of the moon and sun. There's a very similar situation in the Baltic. Anyway, for what it's worth, tides that have a daily pattern of 2 high and low waters are known as semi-diurnal. Tides that have only 1 high and 1 low water each day are known as diurnal tides. And tides that exhibit multiple high or low waters are called mixed semi-diurnal, or mixed diurnal, or more simply, mixed tides. Okay, back to the sun and the moon. As the moon performs its 28-day orbit of the Earth, its position relative to the sun changes. From a new moon on day 0, the moon waxes towards its first quarter 7 days later, then onto a full moon after 14 days, when it starts to wane towards its last quarter, after 21 days, before returning to a new moon on the 29th day. In the northern hemisphere, the lit side of the moon, when viewed from the Earth, is the right-hand side when it's waxing, and the left-hand side when it's waning. When the sun, the Earth, and the moon are approximately in line, at the new and full moon, they exert their maximum combined gravitational pull on the oceans, whereas when they are perpendicular to each other, at the first and last quarter, they exert their minimum combined pull. The moon contributes approximately 2/3 and the sun 1/3. So, at approximately the times of the new moon and full moon, the surface of the oceans rises and falls the most. We call the associated tides spring tides. At approximately the times of the first quarter and the last quarter, the surface of the oceans rises and falls the least. We call the associated tides neap tides. And every 28 days there are 2 sets of spring tides and 2 sets of neap tides. Tide tables in nautical almanacs show neap tide days with blue dates and spring tide days with red dates. You can see here that the range in the early morning of the 21st is 4.4 metres, whereas the range on the 28th is 8.2 metres. Notice the first quarter symbol on the 18th of July and the full moon symbol on the 26th of July. You can see that, in this case, which is pretty typical for areas around the British Isles, neap and spring tides occur a few days after their associated moon phase. Extreme meteorological conditions can also cause tidal heights to vary substantially from predicted levels. Unusually high pressure pushes the surface of the sea down, and unusually low pressure sucks the surface of the sea up. For example, at 10:25 on the 6th of December 2009, the predicted height of tide at Cowes was 2.1 metres. Yet the actual height was only 1.42 metres, 0.74 metres below the prediction. Which was because this unusually deep low-pressure system, northwest of Ireland, was sucking up the surface of the sea there, preventing the tide from rising in the English Channel. At any given location, once in every 18.6-year tidal epoch, and ignoring extreme meteorological conditions, the surface of the sea will drop to its lowest level. This level is called lowest astronomical tide, or LAT. On any given British chart, there is a level known as chart datum, CD, which is a plane averaging lowest astronomical tide across all points on the chart. The difference between chart datum and lowest astronomical tide is very small, and, to all intents and purposes, insignificant. Note that whilst on British Admiralty charts, chart datum is approximately lowest astronomical tide, some foreign charts use a different level. For example, this US chart is using mean low water springs. Charted depths are below chart datum, and ignoring extreme meteorological conditions should be the least depth ever experienced at this point. Take a look at this large-scale chart. The black figures written all over it are charted depths. For example, 12 or 1.5 meters. These are depths below chart datum. Notice how 1.5 meters is written on the chart. Areas coloured green on the chart are above the surface of the sea at chart datum. See the figure 4.3 written here. Notice that the 4 is underlined. This is a drying height and is measured above chart datum. In other words, at lowest astronomical tide and ignoring extreme meteorological conditions, this point will be 4.3 meters above the surface of the sea. Of course, at any time other than the extremely rare occurrence of lowest astronomical tide, the surface of the sea will be somewhere above chart datum. The distance between chart datum and the surface is called the height of tide, HOT. So the actual depth at any charted depth is the charted depth plus the height of tide. In this instance, the charted depth is 1.5 meters, and the height of tide is 6.5 meters, so the actual depth is 8 meters. Whereas in this case, we have a drying height of 4.3 meters and a height of tide of 6.5 meters, giving an actual depth of 2.2 meters. The average height of high water on a spring tide is called mean high water springs, MHWS. On Admiralty charts, everything between chart datum and mean high water springs is coloured green, and everything above mean high water springs is coloured yellow. Charted heights, for example the height of lights, are measured above mean high water springs. The average height of low water on a spring tide is called mean low water springs, MLWS. The difference between mean high water springs and mean low water springs is called the mean spring range. There are also mean high water neaps, MHWN, and mean low water neaps, MLWN. The difference between the two being the mean neap range. Finally, there is highest astronomical tide, HAT, which is the highest the tide will ever go other than in exceptional meteorological conditions. Clearance heights, for example under bridges or power cables, are measured above highest astronomical tide. Clearance heights used to be measured above MHWS, and you will still find some old charts and particularly books that assert this. However, if you assume that the clearance is above mean high water springs, then you will always be erring on the safe side. You can find the heights of mean high water springs, mean high water neaps, mean low water neaps, and mean low water springs for various ports on many charts. However, only the very latest show highest astronomical tide. There is a table on page 12 of your RYA Training Almanac which gives values for the various ports and harbours on RYA charts 3 and 4. However, don't expect to find a similar table in a real almanac. In the real world, but not in the RYA Training Almanac, highest astronomical tide is given at the bottom of each page of tide tables in a nautical almanac. If you don't know the highest astronomical tide and you need to calculate whether you have sufficient clearance to navigate under an overhead obstruction, use mean high water springs, and you will be erring on the safe side. If your draft were 1.6 meters and you wanted to leave a safety margin of 1 meter, then you would, rather obviously, require 2.6 meters actual depth of water. We know that actual depth is charted depth plus height of tide. So imagine, in this case, that charted depth were 1.5 meters, which means that the height of tide required equals 1.1 meters. So, the height of tide required equals draft plus safety margin minus charted depth. In this case, 1.6 meters plus 1 meter minus 1.5 meters equals 1.1 meters. When navigating over a drying area, green on the chart, the height of tide required is draft plus safety margin plus the drying height. In this case, 1.6 meters plus 1 meter plus 1.2 meters equals 3.8 meters. Before anchoring on a falling tide, you need to calculate the minimum depth of water you must anchor in now in order that you do not go aground at low water. If you calculate the height of tide now, let's say 4.5 meters, and subtract from this the height of low water, let's say 3 meters, you know how much the tide will fall between now and low water, 1.5 meters in this case. So, minimum depth to anchor in now equals fall plus draft plus safety margin. If we imagine a fall of 1.5 meters, as per the last page, a draft of 1.6 meters, and a safety margin of 0.5 meters, then the minimum depth to anchor in now equals 1.5 meters plus 1.6 meters plus 0.5 meters equals 3.6 meters. A very similar calculation can be used when you pick up a mooring or come alongside a berth to check whether you will be aground at low water. Clearance at low water equals depth now minus fall minus draft. If we imagine a depth now of 3.6 meters, a fall of 1.5 meters, and a draft of 1.6 meters, then the clearance at low water will be 3.6 meters minus 1.5 meters minus 1.6 meters equals 0.5 meters. Obviously, you want it to be greater than 0. And of course, if you are anchoring in an area with a big tidal range, you're going to need to calculate the greatest depth of water that you will experience during your time at anchor, in order to lay out sufficient anchor cable. If you are using all chain, 4 times the maximum depth is generally accepted as the minimum. You can calculate the rise of tide by deducting the height of tide now from the height of tide at high water. Add the result to the depth now, and you have the maximum depth. Multiply this by 4, and you have the length of anchor cable to deploy. If we need to navigate under a bridge or other overhead obstruction, such as power cables, we need to check that we have sufficient clearance. Remember, clearance heights are measured above highest astronomical tide, or sometimes mean high water springs, which are in turn measured above chart datum. So, for example, if a bridge had a clearance height of 16 meters, and highest astronomical tide were 5 meters above chart datum, then the bridge would be 21 meters above chart datum. A vessel's air draft is the total distance between her waterline and the very top of the mast, including the VHF aerial. Cruising yachts typically have an air draft which is approximately 125% of their length overall, LOA. It'll be a little more for racing yachts, and of course for motor vessels it varies according to design. If it's going to be a close-run thing, check yours very carefully. Your clearance under a bridge is therefore calculated as clearance height plus highest astronomical tide minus height of tide minus air draft. So in this case, 16 meters plus 5 meters minus 2.5 meters minus 16.5 meters equals 2 meters. Another way of looking at this might be to ask, what is the maximum height of tide beyond which a vessel cannot navigate under a bridge, allowing a safety margin? Maximum height of tide equals clearance height plus highest astronomical tide minus safety margin minus air draft. So, in this case, 16 meters plus 5 meters minus 2 meters minus 16.5 meters equals 2.5 meters. You can download a copy of the tidal formulae from the Resources tab. So far so good? Now go on to attempt exercise B. It's only a very short one.